All right, so what we have here is 6 pieces of paper on the ground. We have not quite 6 people standing on pieces of paper. Now, if you have a piece of metal, does it have any charges in it? Why? Because atoms are made of charges, right? What kind of charges are in atoms? Electrons and protons, right. So what we have represented here is 6 metal atoms, 1, 2, 3, 4, 5, 6. All of the metal atoms have a full set of electrons except for one of them on the very end.
They share.
All right. Now, the people standing on the pieces of paper represent electrons that are free to move. Got it?
Yes.
You are an electron, yes. You are an electron. Now, why did I make the paper the atoms and the people the electrons? Why didn't I do it the other way around?
Because the people can move.
Right, the people can move whereas atoms can't, really. Unless you throw the piece of metal. All right, everybody good so far?
Yes.
So, here we go. So what we're going to do is we're going to do a demonstration of how electrons actually move in a piece of metal. So before we do this, we're going to need all of the audience. I'm going to need your help. What I want you to do is I want you to help me out by creating an electric field. All right, so how are we going to create an electric field? We're going to take our field fingers, see field fingers, and the field fingers are going to point that way to that side of the room. Okay, now electrons, we're going to pretend like you weren't making your own field. All right, so everybody, so which way is the field pointing?
Right.
To the, I guess, the left side of the room, right?
Okay.
Now, pointing to the left side of the room. Now, electrons, if you're standing in a field that's pointing left, what way are you going to be pushed? You're going to be pushed to the right. How come?
You like to go opposite of the electric?
Yeah, because electrons are wrong and backward. Right, so, all right, so when I say go, electrons, you're going to move like you would. But here's the rules for moving. You're only allowed to move if there is a free atom to move to. Got it? Okay, ready, set, go. 1, 1,000, 2, 1,000, 3, 1,000. Stop. Okay. So how long did that process take?
3 seconds.
3 1,000.
3 seconds, right?
3 1,000.
So it took 3 seconds. So Carla, how far did you move in that 3 seconds? 1 paper. So 1 atom in 3 seconds. Wouldn't you agree? Macy, how far did you move? 1 atom in 3 seconds. So wouldn't you agree that each of you moved 1 atom in that 3 second period?
Yes.
Okay. How fast did the whole move?
3 seconds.
Wait, what am I talking about? What's this whole thing?
All 5 rows together. All 5 of you.
No, I'm not talking WHOLE. I'm talking HOLE, like one you dig in the ground hole.
5 times.
No, it moves 6 times. 5 times. Right, 5 times as fast. Right. Move 1, 2, 3, 4, 5, 6. 5.
5 times.
5. 1, 2, 3, 4, 5. They move 5 spaces in that 3 second period. Want to see it again? All right, let's do it again. Everybody reset yourself.
Oh, the electric field is
Okay,
just gonna
ready, set, go. Stop. Each person, each electron moved 1 atom. How far did the whole move? Meaning, when I say a whole, I mean the absence of electrons. All right. So, if you had to guess in a wire, say with a typical amount of current, how fast does a typical electron travel in, say, meters? Like say you had a wire this long, it was a meter long wire, and you say you had like an amp of current or something like that in that wire.
Okay.
It would take like hours for them.
How long does it take an electron to get from one side to the other?
Quite a long time.
You sure about
No.
The electrons.
that? Like an electron to travel from one side of the wire.
It's not
Wait,
that
let me
long.
ask a different question. I'm gonna
Very
go
short.
to the light switch. Ready? Here we go. Doink, how long did it take for that light to react? Instantly. How fast was the signal going? Speed of light, right?
Yeah.
So doesn't that mean the electrons are traveling really fast?
No, it doesn't. We just proved it right there. The electrons are slow.
Ha! So, how fast the electrons travel? Individually, very, very slowly.
But as it-
But how fast does the signal travel?
Super fast.
How fast? Speed of light fast. Wait, hold on. Has anyone heard of like the whole idea of speed of light? What? Can you go as fast as the speed of light? No, nothing. Nothing.
Oh, light. Oh.
Nothing can go as fast as the speed of light.
Because
Nothing.
they disappear, like,
Nothing can go as fast as the speed of light, right?
One day.
sound.
So what is the signal that we're talking about moving through the wire?
I'm talking about
The nothing. Right? The nothing is traveling at the speed of light. The whole. You saw the whole move, right?
Yeah.
Started over here and then ended over there 5 spaces later.
Then why doesn't it go faster than the speed of light? If it's nothing.
What's that?
Why can't it go faster than
No, nothing travels at the speed of light.
Why can't it go, if it's nothing, can't it go faster?
Wait, are you talking about the nothing?
The set of
like
The whole is traveling at the speed of light.
Yes, the whole.
Nothing can travel faster than the speed of light.
Yeah.
wait, so nothing can travel.
No, nothing travels the speed of light, right?
No, but nothing can.
Got
The
it?
whole can only travel as fast as the speed of light.
But nothing
Travel
can
slower?
travel at the speed of light.
Wow.
Faster than
You got that? So when you, here's the deal, and you may or may not have learned this last year. I think Hugh and Jack, you had me last year, know this. When we talk electric current, we aren't actually talking about the directions the electrons are moving. We're talking about the directions the quote-unquote positive charges are moving, but the positive charges aren't actually moving. What you're talking really is about how fast the nothing is moving. The whole. And the technical term for this, the materials science term for this is actually HOLE, hole. It's an electron hole. It's the space, it's the atom that is missing an electron.
The single atom, like one atom.
Yeah, that would be a single charge. A single quote-unquote positive charge would be, in actuality, it's the atom that's missing an electron.
So is it nothing that's
It's the ionized, the location of the atom that is ionized. The location that
so within a
started
wire.
here,
Yeah.
and then as the electrons transferred and moved over, the location of the ionized atom is now over there.
So within a wire, is there just one singular ion?
Yeah. So what would be a typical ratio of number of atoms that are missing electrons to number of atoms total? 1 to a really big number. It might be 1 to a
so
trillion.
What makes one conductor better than another?
Good question. Good question. A number of different things. So we're not talking about. Well, you could talk about the fatness of the wire or the length of the
Yeah,
wire,
I
right?
know.
We know that.
Yeah.
But what materials are better than other materials? Think about it. The things that would affect this is how strongly. One of the things would be how strongly that particular atom likes to hold on to its electrons.
Okay, and the stronger the atom likes to hold on to its electrons,
The
less-
harder it is to knock the electrons from one spot to another, which means you get lower currents, right? So yeah, so that's the biggest
So
factor.
that's why we use metals, because they're the best at
Yeah, because metals, if you think about the metal, you look at the periodic table. Take for example gold. It's 79 on the periodic table. That means it's got 79 protons. It's got a huge swarm of electrons around it.
Why is copper
It's-
better than gold? though?
Hold on one second. Take gold. We're going to talk
Okay.
about that in a second.
No, it is.
The easiest thing to think about is if you have a whole bunch of electrons around you, are you really going to miss one? Right? But it has, if you really want to get into it, it has everything to do with the shape of the electron cloud,
Okay.
right? That's the most important part. And it might be that copper takes less energy than gold. And silver is actually, you know what the best conductor is?
What?
On there? Silver.
Okay.
Yeah.
I thought gold was the best, but it was just too
No,
expensive to
gold
use.
is gold is non-corrosive. That's why they use it.
Yeah. Why is silver better than gold? It just is. Why don't we use silver for everything?
It's too expensive.
Wrong. Let's look at the back of this. Let's look at one of these plugs.
Maybe that's yeah. Maybe that's.
All right, in here, these are gold-plated tips in here.
Yeah.
Why is it gold-plated, not silver-plated?
It's
Silver's better.
non-corrosive.
Right. So if these were silver, guess what would happen after about a week?
They would just
It would be coated in silver oxide. If you've ever seen old silverware that hasn't been polished, this would be coated in silver oxide. So when you tried to plug it in, guess what would happen? It wouldn't work because it'd be coated in that gunk. All right. So yeah, you use gold not because it's better than silver, but because it's less corrosive than silver. All right, doesn't oxidize, doesn't rust. All right, so that's that. So everybody got that? So the old idea of current flow is how fast the holes are moving. All right, let's get set back up. Okay, so Nathan, to answer your question, if you read through the notes, I've got a whole long discussion about this.
okay.
Charges flow because something is pushing them, right? Now, if you think about an electron as an individual thing in a piece of metal, an electron by and of itself is just going to jump around randomly, right? So there's a lot of random motion involved with electrons. But if you want to get current to flow from one end of the piece of metal to the other end of the piece of metal, you're going to have to kind of force those electrons to do what you want them to do instead of just jumping around all over the place. All right? And so how do you do that in a piece of metal? How do you force an electron to go a particular direction? Not with magnets.
Do you give it energy or something like that?
Oh, no. We just did a
Connect it to
whole
a
2 months
circuit.
on this.
Connect it
How
to
do
a
you-
battery.
How do you get an electron to move in the direction you want it to go?
You create an electric field.
An electric field, right? You do an electric field. And just like we did earlier, right? If you've got an electric field in a wire, guess what will happen? It'll push all the electrons the opposite direction. Fine. So the key to getting charges to flow is to somehow or another set up an electric field in the wire. All right? Now, you guys all took a test on this yesterday, so you know that one of the way to set up an electric field, or a good way to set up an electric field, is to set up a voltage difference from one side to the other, right?
Yeah.
All right, that'll create your electric field for you. So that's the key to making this work. So you have to have an electrostatic force. So in order to do that, you set up an electric field. And the way you set up the electric field is by setting one side of the wire to be at a higher voltage than the other. That will force the charges to flow. All right, so capacitor. Right, this discussion you guys were just having, you don't have to do it with a battery, you could do it with a capacitor. Right, so let's say you have a charged capacitor. All right, you've got negatives on one side, you got positive on the other, and they're disconnected. That means all along this wire you've got negatives, all along this wire you've got positives as well, right? What would happen if you made a connection between these two wires?
When it discharge, would not be
Yeah, why?
not be good.
Because right now there's
What's this side at?
Positive.
High voltage.
Yeah.
This side's at a low voltage, and then you put a wire in between them, guess what? Now you've got an electric field, which causes the electrons to flow back the other way. Make sense? All right, cool. And actually what I have drawn here is the charges at different points in the wire at a snapshot in time, right? And how long is this current going to last, by the way?
Until the charge will go over.
Yeah, until everything's kind of equalized, right? Until everything's at the same voltage, that means there's no more electric field, agree?
Yep.
All right, cool. So this is what the inside of a wire looks like.
So would that be like the equivalent of if you had like water in a pipe, and then once it all gets to be like the same level, it stops
Yep.
moving?
Exactly. Water in a pipe is a great analogy for this. All right, so in order for charges to move, there must be two things. One, there must be a flow path, and two, there must be a difference in voltage. All right? Now, what I like to think of, the way I like to think of voltage, one of the ways is I like to think of how bunched up the charges are. How bunched up the charges are. Did I show you the battery voltage simulation, what happens inside a battery? All right, we got to show you that because that's... Okay, so how many people have looked at a AA battery before? How many people have cut one open before? Yeah, why don't you cut open a AA battery? No, that's not why. Because inside every AA battery there are little people. There's little colored people. There's a red person, a blue person,
so
a green person, a gray person, an orange person, a yellow person, and a purple person. Inside every AA battery. And if you don't believe me, I'm going to go ahead and show the battery. This is courtesy of fet.colorado.edu, greatest website ever. And except for they don't have iPad stuff yet, but they're working on it. So am I.
They're working.
So anyway, this is actually, if you were to look inside a battery, this is what you would see. You would see a bunch of charges bouncing around on the left and right side, and then you'd see these little colored people. Now, right now, if you look at the battery, you'll notice that there is no voltage difference between one side and the other, and that's not right. So we're going to turn up the voltage a little. We're going to crank up the voltage. What I want you to do is watch what happens when you turn up the voltage. What's happening? Yeah, the little colored people are going and grabbing charges from one side and putting them over to the other side. All right? See that? It's fascinating to watch these little people work because they're so cool. All right? And so there they go. All right? So now what do you notice about the battery?
It's got a lot of charge on one side,
All right.
no charge on the other.
So the job of a battery, if you think about it, is for the little colored people inside to grab electrons from one side and move them to the other side. That's what a battery does. Isn't that cool?
Oh my goodness, I never knew people were batteries.
I know, and this is why you never want to come and open a battery because then you destroy their home. Right? So then I have a question associated with it. It goes like this: what would happen? So this is a battery. Is this battery hooked up to anything yet?
No.
No, it's clearly not because right now there's no current flowing. It's just a bunch of charges on one side, no charges or charges missing from the other side. Therefore, there's a voltage difference. So what we're going to do is we're going to hook up a wire from one side of the battery to the other. You guys ready? Here we go. So we're going to hook up a wire, one side to this side of the battery, one end of the wire to this side of the battery. What would happen to all these electrons over here?
They'd move through the wire back to the other side, and then all the little colored people would take them back.
Right, so that's exactly what happens. The little charges go through the wire, and then these little colored people get upset. They're like, oh my gosh, somebody's putting charges on the other side of our battery. What do we have to do?
We gotta move them.
We gotta move them back again. And so if you keep this wire hooked up, what's going to keep on happening?
You're gonna keep on upsetting the colored people, so they're gonna have to keep on moving those charges.
Right, just back and forth. And does this go on forever?
Yeah.
Does it go on forever?
No.
No, it goes on for a really long time, but eventually what happens?
The colored people are gonna run out of energy.
They're going to run out of energy, right? And that's what we say when the battery is dead. It means the little colored people inside are out of energy. They
So we
die.
throw them out.
All right, and it depends on the kind of the kind of battery. If it's a non-rechargeable battery, it means they're dead. Right? And if it's a rechargeable battery, you just give them more energy. They keep on going. All right, so does everybody understand? So this is one of the analogies I like to use for voltage. Actually, one of the ways of thinking about what voltage actually is a measure of how smushed together the electrons are, or smushed together the electron holes are, right? If you've got a lot of electrons or electron holes crammed together in one location, that means you're at a high voltage, or a big negative voltage. Does that make sense? All right. And no voltage would means they're all kind of spread out evenly. Yes?
How come when you hold double A batteries, like you're coming at the point, you don't get shocked from it? It's just because like there's not.
Wait, says who if you hold a double A battery that you aren't getting shocked?
It's just that there's not enough like amperage and.
Yeah, there's too much resistance. You won't feel it.
Yeah, because your fingers aren't.
Yeah, they aren't very conductive. All right, you guys good? Everybody understand what voltage is? What a battery does? All right, so let's move on.
I wonder if putting a battery in your mouth would really be that bad.
Don't put a battery in your mouth.
They
I
say
used to look them and put them in my Game Boy.
What?
Our YouTube users are kind of be like, why is he talking about sticking a battery in his mouth?
and then they
Oh,
try
the
to
9 volts.
It works. Well, you put a 9 volt in your mouth.
Yeah, you put it in.
All right, so continuing on. Let's go ahead and exit out of here. All right, back to the notes. So, next one, Ohm's Law. Everybody knows this. Ohm's Law. How many people know Ohm's Law is V equals IR? Raise your hand. Okay, technically that's wrong.
Wonderful.
Yes.
Technically it is what?
I equals V over.
I wasn't going to go for, I was going to go a difference in voltage from one side to the other. So technically you should be writing the delta triangle, right? You should be writing that triangle. However, we never do. Why not?
Because usually one side's 0.
Because we are lazy. That's why we never write the delta. But technically, Shiv, every single time, you should write the delta technically. And we never do. So in physics class, anytime you see V, you should be thinking delta V in Ohm's law. All right, so let's see, and that's what this discussion is. This is a big oops. It's an oversight. It's actually just sloppy. I too am lazy, and from now on I will usually say voltage when I really mean difference in voltage. Got it? All right. If you don't know which I'm talking about, just ask. Good? All right, here we go. Last one, resistance. What is R? Well, resistance is a measure of how hard it is for the charges to get through with a given voltage, right? So resistance is measured in ohms. Let's see, we did the FET battery voltage. We're going to skip the micro.magnet.fstu.edu and just kind of move on. How charges flow, we already talked about that with our demonstration. All right, so this shows time lapse. At time 1, the hole is here. At time 2, the hole is here. How come?
Because an electron moved over into the original hole.
Right. Last one. Positive charge flow is really the direction the hole is moving, not the direction the electrons are moving. Last one, drift velocity. This is an equation that you'll see in the homework. It basically says the total current flow. This goes back to Nathan's question. Why are some materials better than others, right? Though that's related to this equation. The current flowing in a wire would equal the total number of charge carriers per volume times the charge of each carrier, which in this case is an electron, times the drift speed, the random drift speed of the electron, times the cross-sectional area. All right, so the more charge carriers you have per volume, the more current you get. And then, of course, the faster on average they're drifting across, the more current you get. The fatter the wire, the more current you get. Right, okay, and that's it.